Okay, before continuing, I wanted to go over the action potential a little bit more. And I drew this, and this is a picture of an action potential. And we have our voltage gated channels, their states being shown in green. So again, here's the voltage gated channels being shown in green. And purple, you have the voltage gated potassium channels. And you have O for open, C for closed, and I for inactive. Now, in the picture that we have here, this is an action potential where the x-axis is time in milliseconds. And we have the action potential going through its depolarization phase right here, and then its repolarization phase right here, and a little bit farther down, and you're going to have a hyperpolarization phase right here. I didn't write it down, but it's going to be right here, okay? And in green, we have the states of the voltage-gated sodium channels. So the voltage-gated sodium channels, let me scroll down, you're going to have them going from closed to open, then open to inactive, and then they'll be inactive for this whole area right here. And then once the potential in the membrane has gone to resting potential, they move from inactive to closed, right? Now, as for the voltage-gated potassium channels, they're in the closed state right here in the depolarization phase, at least halfway through it, and then they start to move from closed to open right here, right? And then, halfway through the hyperpolarization phase, they start to go from open to inactive, and then once the resting potential has been reached, they go from inactive to closed, okay? Now, we're going to look at the same thing, but now our x-axis is going to be distance. So remember, this will be a mirror image of what we have right here. So let's scroll down and look at that. And here's our action potential where the x-axis is distance. Now, in this case, the depolarization phase will be here. The repolarization phase will be here, and hyperpolarization phase will be right here. And let me scroll up so you guys can see the hyperpolarization phase right there. Okay? And the same type of notations, right? Since this is a mirror image, everything would be on the opposite side, right? So here, during the depolarization phase, just like above, we have the voltage-gated sodium channels going from closed to open. We have them here going from open to inactive, and then they're going to be inactive for this whole part here. And then once the membrane is repolarized back to its resting state, you go from inactive to closed. Now, as far as the voltage-gated potassium channels are concerned, they're going to be in the closed state right here. They'll be in the closed state all the way through here, right? And they'll be going from closed to open right here during the repolarization phase, all the way over here, right? And then they're going to go from open to inactive right here, and then they're going to go from inactive to closed once the resting potential is reached. Now, what you should notice when we draw it out like this, because the action potential is now, this is like on the membrane, how it looks, it is moving in this direction. Why is it moving in this direction? Because this whole area right here, and let me see if I can choose another color. Right here, this bit right here, right? This, you're past the threshold needed to start having those voltage-gated sodium channels go from closed to open. So this whole area right here is going to start getting depolarized right here, right? And you're going to have all those voltage-gated sodium channels go from closed to open. And all the way over here, all you have are voltage-gated sodium channels that are in the closed state, ready to go to the open state once they start feeling that depolarization happen to the membrane. So the front part of an action potential is depolarizing the membrane in front of it, while in the back end right here, well, the voltage-gated sodium channels are in the inactive state. And the membrane is permeable to potassium because the voltage-gated potassium channels are basically in the open state, right? So that patch right there, that part right there cannot become depolarized at all because there's no way to make it permeable to sodium. So I hope by looking at this, you can see why an action potential will travel in a certain direction. It's not ordained that it must travel in this direction. It's just because of the way those voltage-gated sodium and potassium channels work, that once you initiate it on one end, it has to travel to the other end and it won't go backwards. Okay? Actually, if you want to take this one step further, if I had an axon, here's my axon, right? And what I did was I artificially went ahead and depolarized the membrane right in the middle of it. Like I depolarize it by artificial means. What will happen is an action potential will flow in this direction and an action potential will flow in this direction. It is just because of the way a neuron works that you have the cell body, the soma and the dendrites right here, and the axon going off of it, right, in this direction to the axon terminals and etc., that the initial depolarization event happens way in the beginning, so you initiate an action potential and it flows in this direction. But if I artificially induce an action potential in the middle, meaning I depolarize the membrane in the middle of the axon, an action potential will be generated which will flow in both directions. Alright, so enough of that. The next thing we're going to talk about is myelination of axons. The axons of many vertebrate neurons are insulated by myelin sheaths. This insulation is required since in many cases axons are long in length, and without insulation the electrical signal, the action potentials, will dissipate as it travels down the axon. What does that mean? We can use this picture here, and let me erase this thing right here. What will happen is once an action potential is initiated, it will flow down with a certain amplitude. And since the axon can be about 1 meter long, especially for central nervous system neurons, if it's not insulated, the amplitude will start to decrease and decrease until it disappears. Okay, that's just the way it works. It just starts to lose its intensity. And once it loses intensity, then those voltage-gated sodium channels, that patch of membrane, will not reach the threshold necessary and you get fail initiation. And this problem is solved by insulating those axons with myelin sheaths. Myelin sheaths are formed by glial cells which wrap themselves around axon segments. So here we have a couple of pictures of it, and you can see that a myelin sheath is nothing but a glial cell that wraps itself around the axon, and that's being shown here. That's a single cell. It's sort of wrapping itself around. It has a nuclei and etc., and it's wrapping itself around the axon. And what you have is little segments in between these nodes of Ranvier where the axon is exposed, okay? And this picture is just the electron micrograph of that, an axon, and then you have the glial cell wrapped around it. And here is a picture showing you that you have the glial cell and you have the myelin right around it, the myelin sheet, like that, and like that. And then you have an exposed node of Ranvier right here. Now, what happens is that for those areas that are covered by the myelin sheet, by the glial cells, all the channels and everything are blocked because you have this membrane of another cell wrapping itself around that area. So all those voltage-gated sodium and potassium channels are going to be blocked. So what does this do? So myelin sheaths has the effect of decreasing capacitance and increasing resistance across the axonal membrane. The decrease in capacitance comes from increasing the width of the membrane, and the increase in resistance comes from myelin blocking all ion channels on that patch, including the potassium leak channels. All that is saying is that resistance is coming from the fact that charge cannot easily move across the axonal membrane anymore because those ion channels are blocked. And that's the classic case of resistance. When you have something, a material that's highly resistant, charge cannot move across it very well. And capacitance is also decreased in this case. This has the effect of increasing the width of an action potential dramatically, making it broader. Since the only places where an action potential can be generated are at the nodes of Ranvier, because the nodes of Ranvier are the parts that are not myelinated, so the voltage-gated sodium and potassium channels are available, the action potential jumps from one node of Ranvier to the next as it travels down the axon. This jumping from node to node maintains the strength of the signal and also has the effect of increasing the rate by which the signal travels down the axon, the signal being the action potentials. So all that is happening is, if here's my axon, okay, and I have myelin around here like this. Here's one myelin sheet, here's another, here's another, and here's another. And the only places I have voltage-gated sodium channels and potassium channels available are right here in red. Okay? Let me go ahead and put another one here. So what will happen is the action potential will be generated here, and it will just be very broad, and it will come all the way over here, right? And you can imagine that it is you have the hyperpolarization phase behind it. And once it reaches here, now these voltage-gated sodium channels right here, they feel the depolarization, and they start to go through the depolarization phase and generate another action potential. So then you get another one generated right here, and it's going to be broad, and then you get another one generated right here, and it's going to be broad, and you get another one generated here, and it's going to be broad, and it's just going to move down in this way. So the green thing that I'm showing you right here, that's a single action potential as it moves through time. So first it's here, so we can say T0, and let's say T1, T2, T3. This is moving down in this manner. So it's sort of like a bump up, then goes down, then bump up, then goes down, and bump up, and goes down. And this has this effect of not only making the action potential move more quickly down the axon, but it also maintains this amplitude. And I did not do a good job of showing that because this one is a little bit larger. So let's erase it and make it like that. So they're all going to be about the same amplitude. So it doesn't lose its amplitude, right? And it just maintains the strength of each action potential as it's moving down. Okay? Now, the whole thing about capacitance and resistance, the reason why I put it in here, it's not that important for you guys. I'm not going to ask you a question about that. The reason why I put it in here is because I want you guys to know that what you learn in Physics 2 is very important to neuronal signaling, and neuronal signaling is very important to the biology of multicellular organisms. So just put that in there for you guys to see. But all the effect that it has is that it broadens these peaks. They're much broader than they would be because without the myelin, they'll be something like this, right? So it just broadens the peaks so that they can reach each node of Ranvier. The importance of myelination is dramatically demonstrated by demyelinating disease, multiple sclerosis, in which the immune system destroys the myelin sheaths in some regions of the central nervous system. In affected regions, nerve impulse propagation greatly slows or even fails, often with devastating neurological consequences. So in MS, what happens is the immune system starts attacking these glial cells and killing them. And once the myelin is removed, now the signal that's initiated at the soma and the dendrites, it travels down the axon, but then it loses its strength and it never reaches its destination. So you start to have paralysis and all kinds of other issues. And it's as with most autoimmune diseases, it's a degenerating disease where over time it gets worse. Okay, so the next topic we're going to talk about is synaptic connections and neurotransmitters and transmitter-gated channels, and we're going to leave that for another video. Okay guys, thank you. Bye-bye.